So this video is going to talk about the introduction to network flows, including sources and sinks. So this is all the background information that you need to deal with for section 4.3. The only background information that we'll skip out on this time is going to be talking about cuts. So to start off with, let us look at a motivating example, and we'll start off with a directed graph. Okay, and let's go ahead and assume that this directed graph actually models pipes that are going to hold water. So for example, that edge A to B right there, this would represent a pipe flowing from whatever location A is to whatever location B is. It's going to let water travel along it, and the water is only going to travel in the direction A to B. Okay, so that's the background. Please notice we right now are ignoring capacity of how much water that these pipes can actually hold. We're just looking at the actual system itself of where those water pipes are located with these edges and then in which direction the water can flow. So there's a couple of things to notice about this particular directed graph that we're then going to extrapolate out and apply to any directed graph. And specifically, we want to look at the vertices. So take a second here, look at these 6 different vertices. And what you should notice is that there's different things happening to these different vertices based on the directions of the directed edges. So first of all, let me direct your attention to 2 special vertices A and E. Notice for both of these vertices, all of the edges that are incident to the vertices A and E are leaving the vertices A and E. So this is special here in terms of the water for water pipes. This would represent where maybe you turn on a faucet and pump water into the system. If this was modeling some sort of water pipe situation that you built, maybe on a small scale, this is literally where you turn on the faucet. If this was modeling something like on a city, maybe A and E represent 2 different water reservoirs that the water enters your system here. These guys are called sources because this is where your stuff that you're caring about that's going to travel through your digraph is going to enter your system. Now, the other special vertex in this graph is down at vertex C. Here, it's similar to the specialness that we saw at vertices A and E, but it's in reverse. So here, all of your directed edges are pointing in towards C. Okay? All other vertices that are currently not highlighted, so vertices B, D, and F, are some combination of directed edges both entering and leaving the vertex, and that's standard. But these guys are vertices A, E, and C. These guys are our special vertices. So vertex C is called a sink, and this is where if the water's flowing through these pipes, the water would come into vertex C, and then it couldn't go out again across the digraph. So this is where your water would be leaving the system. In terms of water, I picture the sinks as where the water would drain out, if you will. Okay. So here's the technical terms. A source is a vertex where the in degree is 0. It only has an out degree. A sink is a vertex in your digraph with an out degree of 0, and it only has an in degree. And in terms of what we just talked about with our example, if we're thinking in terms of water and water pipes, a source is where the water enters the system like a faucet. A sink is where the water drains out of the system like an actual drain, if you will. So now that we know what a source and a sink is, let us look at a couple of more details. So again, we're going to go ahead and assume that these water pipes can hold whatever water we plan on pumping through the system. So let's actually start pumping some water through our system here. So let's suppose that we actually want to push some water into our system. So at the source A and at the source E is where we'll be able to have water entering the system, because those were representing like our faucets, okay? Or our water reservoir if we're thinking large scale. So let's go ahead and push 5 units of water into our system at vertex A. Maybe those 5 units are something like 5 gallons. Maybe those 5 units are something bigger like 5 million gallons, depending on your scale here. We won't focus on the units. We'll just put that this is 5 units, and then at E, we'll go ahead and push 3 units of water into the system. So here, when we get at vertex A, once the 5 units are entering the system, notice we have 2 edges where those units of water can go down. Now, the water can divide, and depending on how you got the system physically set up, it may divide in different ways. Maybe down the edge AC, no water pumps down that edge. Maybe it's closed for maintenance. But maybe it's actually semi-evenly divided. I'll go ahead and say, let's suppose 3 units of water gets pumped down the edge AC and 2 units of water pumping down the edge AC, 3 units of water pumping down the edge AB. Now, if we then look at the vertex B, notice we have the water, 3 units of water coming into B, and only one way for that water to leave. So assuming that we actually have some water pressure here, well, all 3 of those units of water have to travel from B up now to vertex C. Please note the other assumption that we're using, not just the assumption that the pipes can handle whatever water we pump through them right now. We'll adjust that in the future in just a second. But we are also assuming that there's no sort of leaky pipe situation. There's no bag connection and water's actually leaking out here at B. Okay. So now let's go over to the other side of the graph. Over at vertex E, we can go ahead and divide up that flow, that inflow of water in a couple of different ways. Let's go ahead and put 1 unit of water going down E to D, and then 2 units of water going down from E to F. We then look down at vertex F, 2 units are flowing in, so we are still assuming that there's no leaky pipe situation. We only have the water pipes that we visibly can see with the edges, so that means 2 units of water would then turn the corner and pump over to vertex D. Now, here's the fun part. At vertex D, we have 2 different pipes coming in, and currently a unit of 1 and 2 on those 2 different pipes, so a total of 3 units coming in, which mean all 3 of those units are going to pump over there to vertex C, or our sink. So, a couple of things to notice. First thing is, if we look over the entire graph that we have right here, the total flowing in from all of our sources, the 3 and the 5, is a total of 8, does in fact match the total flowing out at our sink. We only have 1 sink. Notice the 2, the 3, and the second 3 also sum to 8. As long as you don't have a leaky pipe situation, which we are not going to have, that is true in any sort of these situations where you start pumping something flowing through your digraph. Now, the other thing that we did, again under the assumption of a non-leaky pipe situation, at each one of our vertices, specifically the vertices that were not sources or sinks, we had what? We had the total water that was flowing into that vertex equaled the total water flowing out of that vertex. So for example, here at D, the total flowing in was 1 plus 2, the total flowing out was 3. Now, what we've just put on this graph with modeling the water coming in at vertices A and E and leaving at vertex C is something called a flow. Your textbook calls it an AZ flow, where the A is tagged as your source and your Z is tagged as your sink. Technically, you can have several sources and several sinks. In terms of how we'll deal with flows, we'll actually do an original adjustment or initial adjustment to get it down to 1 source and 1 sink, but we'll talk about that in class. Okay. So what a flow is it is actually a function where the inputs are edges and then the output is the flow number, or how much of your stuff, in our example previous, how much water is actually able to be pushed through that edge. So here's some of the properties that you have to have in order to be a flow. First of all, your value is going to vary between 0 and the capacity of the edge. This capacity of the edge is exactly the same as the weight of an edge that we've had in our previous algorithms. Here in a flow, it's called capacity because you're typically modeling something like water flowing through pipes or electricity going through wires or something like that. Okay. The other thing that you have to have for any vertex that's not a source or a sink, the total flowing into that vertex is always going to equal the total flowing out of that vertex. And these two points right there are the main 2 things that you need to worry about. The last 2 properties, or the last 2 things you need in order to be a flow, are actually cleanup. So maybe your graph isn't beautifully put together. Maybe you have some extra edges that you shouldn't have had in your graph. They're technically there, but they're not really going to be incorporated into what you're going to be using. And this is what happens. Suppose you have a source. Remember, a source is where all the stuff is coming into the graph, and you actually have an edge going into that graph in the wrong direction. Well, if that's going to be your source for your network, what that means is you need to make sure that the flow there is 0 on that backwards edge. Same deal with a sink. A sink is supposed to be where everybody goes and then never leaves. Well, suppose you have an edge that's going in the wrong direction. It's trying to get out of a sink. Again, in that case, you want to make sure that your flow is actually 0. If you have a properly put together network to start with, you shouldn't even have to look at these properties 3 and 4 or criteria 3 and 4. It should be automatic because you don't have those type of edges. The other thing that people look at when they talk about flows is they look at the value of the flow or the total value of the flow, and this is tagging or calculating the total amount of stuff that's going through your digraph. So for example, if we talk about water, this would be the situation of the total amount of water that was pumped into your digraph from across all your sources. Now, since the total amount of stuff being pumped into your digraph from all your sources equals the total amount leaving your graph from all your sinks, you could actually look at your sinks as well and count this up. One property of this is when you calculate that flow or value of your flow, where you do sum up all of the amount that's coming in from all of your sinks, it will turn out to be always less than or equal to the capacity of those edges that are attached to your sources. Excuse me, I said sink before. I want to say sources. And notice these are just the technical terms that listed out what we had just talked about in our previous example. So let's put this all together. In terms of the main algorithm of section 4.3 that we're going to be looking at, we're going to initialize that algorithm with an initial flow. There's two ways that you could be given this flow. One, you might be asked to create an initial flow, or two, you might be given a potential initial flow and you need to verify that it actually is a flow. So if you're given a situation and you want to verify if what you're given actually is a flow, here's the checklist. First of all, in terms of what you're given, you'll be given a directed network, and it'll look similar to what we have right here. So notice this is the same digraph we've been looking at over this entire video. What I did here is you now have additional labels on the edges. And here's what those labels mean. Notice how there's two numbers. One number's inside the parentheses, one number's outside the parentheses. The first number that's outside the parentheses gives you the capacity, or if you prefer, the weight of that edge. So in terms of this graph that we've been saying models water pipes, this capacity would be how much water that pipe could actually handle. Now, inside the parentheses, that's the actual flow that you have. That's the value or how much water we're physically trying to push through that segment of pipe, that edge. Okay. Now, to check to see if this whole thing actually is a flow, you'll go through and check to make sure that those numbers inside the parentheses actually meet the criteria that we need to be a flow. So here's the list of those 5 criteria that we just had. So the first one says that you need to make sure that your flow is between 0 and the capacity of the edge. Now notice what that means in terms of these numbers right here. That means the number 2 here, which is the flow on edge AC, needs to be between 0 and 3, the capacity of edge AC. So literally we're just going to check is the number in the parentheses between 0 and the other number given on that same edge. So if we look at 3 and 2, 2 is smaller than 3, so we're good. 3 is equal to 3, so we're still good there. That actually tells you that the flow from A to B is at maximum capacity. So then we look at the edge here, B to C. 3 is smaller than 5, that's good. D to C, 3 is smaller than 4, so we're good there. E to D, 1 is equal to 1, so that's at max capacity, but we're still good. E to F, 2 is equal to 2, so maximum capacity, but still fine. 2 is smaller than 4, and that's perfectly fine. So what does this tell us? This tells us that we do meet that first criteria. Now, second criteria, and this one is the one that actually takes a little bit more work, and this is the main one actually that you have to check. So this one says that you check every vertex that is not a source or a sink. Now remember where our sources and sinks were. Our sources and sinks were at A, E, and C, so we're literally just going to be checking vertices B, D, and F for this second criteria. So at each of those 3 non-source, non-sink vertices, we're going to go ahead and check if the total in equals the total out. So at B, total in is 3, total out is still 3. Notice you're only now comparing your numbers inside the parentheses. So at vertex B, we're good. Okay. Next, we go over to vertex D. Total in is 1 plus 2, so that's total in is 3. Total out is 3, so 3 equals 3. We're good there too. At F, total in is 2. Total out is also 2. Again, we're only looking at the numbers inside the parentheses, so that one works as well. Now, criterion 3 and 4 are looking at your sources and sinks. If you look at your sources, so vertices A and E, notice here this says if you have an edge that goes into your source. We don't have an edge that goes into the source in either one, so by default we're good. Criterion 4 says your sink, so we'll look at vertex C. This says if an edge leaves vertex C. Nope, we don't have that, so we automatically have that fourth criterion. And the last thing that I would recommend looking at, not part of the definition of a flow, but definitely something that helps you check to see if the flow is working correctly, look at the total amount coming in from all of your sources. So at A, we pushed in 5 units. At E, we pushed in 3 units. So we pushed in a total of 8 units from our sources. We check to see if that's the same amount leaving the sink. So at our sink, we have a flow of 2, 3, and 3 coming into that sink. So 2 plus 3 plus 3 is also 8. So we are good there as well. Which means, what's our conclusion? Yes, this actually was a flow. No, we created this exact same flow just a little bit ago, so it shouldn't be a surprise that we got an actual flow. Now, last thing that you'll often be asked about is, hey, what's the value of our flow? And the value of the flow is, if you look at the sources, the total amount that you've pushed into your system from your sources. So this would be the 5 units from vertex A and the 3 units there from vertex E, add them together, and that 8 is the value of this particular flow.